In this video, we're going to explore the applications of counting methods to probability. So what that means is we're going to focus purely on the exam style questions. So if you haven't already checked out the lecture content on this topic, then please do so using the link in the description. For those that don't know me, my name is Chris Ionazoni. I used to work as an engineer for a defense company, and I left that to start a career in tutoring. Now I make these videos to help VCE students do the best they can in math methods. Three-letter product codes are to be created using the following group of letters. If no letter can be used more than once, what is the probability that our product code starts with a vowel? Well, if we're following the framework, then the first thing we should do is try to calculate the total number of possible product codes. So in this case, the order matters. The code ABC is different to CBD. Hence, we're going to use permutations. There are 8 total letters and we're selecting 3 of them. After we simplify all the factorials, we come to find that there are 336 different product codes. The next step is to figure out how many possible product codes are there that start with a vowel. And in this step, it's easiest to focus on the restriction first. So, we have 3 slots to fill in total. There's only 2 vowels in the list of letters, hence the number of choices that we have for that first slot is going to be 2. The remaining 2 slots have no further restrictions. So the second slot is going to have 7 remaining choices, and the third slot is going to have 6. The final step of the framework is just to perform the division. 84 divided by 336 is going to get us to the probability of a quarter. What if we wanted to find the probability that the letter C was chosen? Well, there's actually 2 ways we could look at this, and the first method is to go back to thinking in terms of slots. If the letter C must be chosen, then there's actually 3 possibilities here. It can either be chosen in the first slot, the second slot, or the third slot. In the first instance, we only have 1 choice for that first slot, since C must be contained in the first slot. Then we're going to have 7 choices for the second slot and 6 choices for the last slot. The other 2 instances are actually pretty closely similar. In fact, the only difference between the 2 is that the order in which the numbers are written is different. These are mutually exclusive outcomes. They cannot all be happening at the same time. Hence, we're going to use the addition principle to add each of those scenarios together. And once again, we're going to turn that into a probability by dividing by the total number of possible product codes. We're going to borrow that number from when we calculated it earlier. Another approach is to use complement probabilities. So instead of finding the probability of selecting the letter C, we can instead find the probability that we don't select the letter C and then subtract that from 1. This actually ends up being a little bit easier since we can calculate that one using permutations. If we cannot choose C, then all that means is that our number of total letters goes down from 8 to 7. And if we use our permutations equation, now with n equals 7, we're going to find the number of combinations that exclude C. We're then going to turn that into a probability by dividing through by the total number of possible product codes. And then we're going to subtract that from 1 since we were using complement probabilities. A team of 7 players is to be chosen from a group of 6 men and 7 women. Find the probability that the team contains more men than women. First, we need to figure out the total number of possible teams. In this case, the order doesn't matter. A team of Jack and Jill is no different to a team of Jill and Jack. Hence, we're going to be using selections. There are 13 total people and we're selecting 7 of them. After simplifying all of the factorials, this is going to come to 1,716 possible teams. The next step is to figure out how many teams have more men than women. There's actually 3 possibilities here, and each of them are mutually exclusive. Hence, we're going to solve each scenario individually and then add all the results together. If we're calculating for 6 men and 1 woman, then of the 6 total men, we're selecting 6. And of the 7 total women, we're selecting 1. These are choices that are made in sequence, so those 2 things will be multiplied together. Similar can be said for the other 2 scenarios. The only thing that's changing is that the number of men is decrementing and the number of women is incrementing. After we add up all those combinations together, we get to a total of 658. And the final step is to divide through by the total number of possible teams, thus turning it into a probability. And that gives us a probability of 329 over 858. A pizza can be made with any of the following toppings. If the pizza must contain at least 1 topping, find the probability that that pizza contains ham. So first, as always, all we're going to do to start with is to figure out what the total number of possible combinations are. And in this case, there are 8 total toppings, and we have 2 choices for each topping. You either choose it or you don't. And since these are choices made in sequence, we're going to multiply along together. There is one thing to watch out for though. The way we've currently done it implies that there is a possibility that the pizza contains no toppings. So, since we're assuming that it must contain at least one topping, we're going to subtract that one combination that contains no toppings. The next stage of the framework is to figure out how many of those combinations come with ham. And the good news is that nothing really changes here. If we previously assumed that there were two choices for each ingredient, well, now there's only going to be one choice for the ham ingredient since you have to include it. And finally, we're just going to divide the two together to obtain our probability. This one here is going to be a hard one. A jar contains 5 red, 2 blue, and 3 green pieces of candy, and 4 pieces of candy are going to be taken from the jar. Find the probability that at least one red candy is selected, given that at least one green candy is selected. This is an example of a conditional probability question, so we're going to start by writing the conditional probability equation. It's usually easiest to start with the denominator, and by following our framework, we know that we have to start by finding the total number of possible combinations. The order that we're selecting the candies in is irrelevant, so we're going to be using selections. There are 10 total candies and we are selecting 4. Next would be to find the total number of combinations that contain one or more green candies. There's actually a couple of ways we could do this. If we're trying to find one or more green candies, then the typical approach might be to just find the total number of combinations that contain one or more green candies. So that means you would find the probability of 1 green, add it to the probability of 2, then 3, then 4 green. There is, however, a better way, and that better way is to use complement probabilities. So instead of wasting all of our time calculating a large sequence of probabilities, we can instead find the probability of getting no green and then subtract that from 1. So if we're selecting no green, then all that means is we're going to remove the 3 greens from the total of 10, giving us a new total of 7 to pull from. And then finally, to obtain the probability of getting no green, we're just going to divide through by the total number of possible outcomes. And then we're going to subtract that number from 1 to get back to the probability that we wanted, which was to get at least 1 green. Now that we've found our denominator, it's time to find the numerator. The intersection between getting 1 or more red and 1 or more green just means you want both 1 or more red and 1 or more green. So we're just going to use the same tactic as before, using complement probabilities. So if we're going to select no red, then the new total number of candies is going to be 5, since there were 5 red and we're removing that from the pool. We actually already looked at what it takes to get no green candies, so we're just going to add this number of combinations to the number of combinations that contain no green. That's going to give us the probability of getting no green and no red after we divide through by the total, and then we're going to subtract that from 1 to finally get that intersection that we're looking for. Okay, well, we have our numerator, we have our denominator. All we're going to do is perform that division. Just a quick note on how to do this. If you have fractions stacked on fractions, it can be very hard to see how that simplifies down. So make life a little bit easier by using a division symbol. A team of 3 students is to be selected for a table tennis competition. There are n eligible students, 6 of which are year 12 and the remainder of which are year 11. Find the probability that only one year 11 is selected for the team. So to start out with, we're going to figure out the total number of possible teams. In this scenario, the order doesn't matter. A team of Jack and Jill is, again, no different to a team of Jill and Jack. Hence, we're going to be using selections. There are n total people to choose from, and we're selecting 3. Simplifying these factorials isn't any different to what you're already used to. It's just that these ones have n in it. You're still going to be expanding the numerator and denominator, and then cancelling through all of the like terms. Now, we need to find the total number of combinations that contain only one year 11 in it. That means we're selecting 1 year 11 and 2 year 12s to make up that team of 3 people. There are 6 total year 12s and we're selecting 2 of them. There are also n-6 year 11s and we're selecting 1 of them. The reason it's n-6 year 11s is because of our total n number of students, 6 of them are year 12s. So to find the remaining number of year 11s, you're going to remove those 6 year 12s from that n total number of students. All we're going to do from here is simplify that expression down until it's a little bit nicer to work with. Then, to find our total probability, we're just going to divide the 2 terms together. This is really all we can do with it for now, since there's no numerical way to solve for n. That all changes now. In this case, we're told that our previous probability was greater than 0.5, and we're told to use that information to figure out what the possible values of n must have been. Well, all we're going to do here is apply that inequality greater than 0.5 and then solve using the CAS. In this case, we're actually going to get 3 different domains. This is where we have to do a bit of a sanity check. Well, we can't have a negative number of students, so the first domain is clearly invalid. We also can't have a decimal number of students either, So we're going to take our decimal and then just round that up to 8. Be mindful of the inequalities here. We only wanted to exclude the 7.47, not the 8. And lastly, we're just going to remove all of the non-inclusive values. This means the 1 and the 2 are going to be invalid, and that also includes the 10 as well. So finally, the only valid answers are going to be 8 and 9. If you found this video helpful and would like to see more, I actually have all sorts of additional resources available for free on my website. Just click the link in the description and you can access them here. And if you'd like my personal help, then consider signing up for the tutoring program. I offer the first 2 weeks free of charge so you can get a feel for whether or not this will be a good fit for you. Otherwise, I'll see you in the next video.